it doesn't matter. Because people I've been noticing have been just watching the main sessions, so not really the introductory course. Yeah. So anyway, I really look forward to seeing you tomorrow. A lot of you guys. I know George, you offered to be part of the panel, and even if you don't want to be part of the panel, I would like you to even on the comment, because there will be like a lot of comments on the chat, questions. So some of the questions, I'm sure you will be able to address them instead of taking time for on the thing for me to address them. So it will be great for you. Okay, so Barry is in. Thank you. Yes, I saw the answer. Thank you so much. So everyone else in here, especially those of you online now, Claudia, Amir, everyone online now, really, Dimitri, everyone, it will be great to have you guys. Okay.
Yes, I would like to encourage younger women, people from other countries and so forth, so that it's as most diverse panel, as diverse as the group of people we do have.
Yes. It will be so thing, because I know a lot of people, even those who cannot attend the live sessions, they do watch on YouTube, because I get the feedback. They reply to me asking questions and these things. So it would really be nice to have your view and share your experience with your advice to others going through or looking to get into these things. Okay, so that's it. Yeah, so this is what I was saying. I hope maybe it's less confusing now. So this is what I was telling George on the thing. It was a bit confusing, the definition I gave the thing, because I did this for k greater than 0 and then g to the minus k. So that would have been like the thing, the positive, not on that section. This one is okay. This one is okay. It's just on this one. I think the issue was, the ambiguity was on this one mostly, right, George?
Yes. Now it's perfect.
Yeah, now it's better. So this is the module. I mean the absolute value of k. So that means it's the positive power of the inverse. Okay. Yeah. Maybe I should have just said for k negative. Then I would, the other thing would have worked if I have used natural language as opposed to, trying to be formal. Yes. So, yeah. So I'm pretty sure most of you already figured it out. So yeah. So just the thing. And thank you, George and Bob, for bringing that up. Okay. So let's just recap where we were left off. Okay. Which is the cyclic group structure. Okay, so we found out that a cyclic group is a group generated by some element. Okay, so that's a cyclic group, and we call this element a generator of the group. Okay, and we've seen here an example in the case of the integers. The integers under the addition, right? That's a prototype of a cyclic group, and this group is generated by 1 and -1, right? And this tells you that obviously a cyclic group can be generated. This is already hinting you can be generated by more than one element, right? Because the inverse also, I think there was somewhere homework saying whether the inverse of a generator, the group inverse of a generator is also a generator. Yes. Another thing is, consider the this group here, the set of integers. Or the set of even integers given by this, like this 2k, such that k is an integer. This is obviously a cyclic group generated by 2, right? Because 2z, any element of the thing has this form, right? So it's generated by this single element. And something else very interesting that we found is that obviously this is being a subgroup of Z motivated us to ask this question. We'll get to the answer of this. I don't know whether you took this challenge, but you will find the answer in a minute. Is every subgroup H of a cyclic group G also cyclic? What was the consensus on the thing for everyone on the chat? Anyone can throw in a hat. I know George probably already. George and Bob will probably already figure it out. Anyone wants to throw in the hat? Otherwise, I have to ask George.
I think that once cyclic is part of your structure, you can't get rid of it by taking a subgroup.
Okay, that's interesting.
So yeah, I'm taking the negative thing. Could it be possible that it's not? But I don't think so.
Okay, that's interesting. Does anyone else want anything? Yeah, I want anything. Want to say anything? Add any comments to that? Is every subgroup of H? Sorry, every subgroup H of group G also cyclic? We'll find an answer actually in a minute. Okay. For the time being, let's go and see another example. In this case, a finite example. Obviously, Z is an infinite group. So let's say, yeah.
The chat consensus is agreeing with it.
Okay. Interesting. I will also ask. You will see some twist in anything the other way around. I will ask this question again whether. It's okay. It's more convenient to come to this question later. Yeah. So let's consider a finite example of a finite group. So let's consider Z or Z6 as in Americans you read it Z, right? Z6 under the addition mod 6. So this is cyclic group, I claim. And I claim the generators are these. Okay, you can also correct me on this. I think we came to the conclusion to that. And
yeah. 5 is equal to -1 mod 6.
Okay. The same with interestingly, this is a very interesting case. I want you to look at the indices here. Okay, so this is Z6, this is Z7. In particular, when things are prime, just pay attention to see what's happening here. Okay, so for Z7, obviously 7 is a prime number. I'm already giving away some stuff. You can see the generators are pretty much everything except the 0, right?
There's a little typo there.
Yeah.
1, 2, 2, 4, 5, 6.
Okay. Yeah, there is a typo here. Yeah, I knew there was a typo here. Yeah, but I'm glad I wrote this because this we already show. So there is 3 here. Yeah, sorry for that. I will correct this before I upload the slides. Yeah. So interestingly, very interestingly, the thing, everything else except the 0 element is a generator. Okay. Now there's also a bit of a spacing thing here. It's not a problem. I'll correct this. Now this motivates us something very interesting because in here we have only 2 generators. In here we have like how many generators? We have 1, 2, 3, 4, 5 generators, right? Or is it 6?
6, everything except 0. 6 out of the 7.
Except 0, because this is a 7, right? Yeah. You see, I'm already like confused in counting. This is what happens when you dive too much into abstraction. When you see concrete stuff, it confuses you, right?
Yeah.
There was a story about Grothendieck, right, saying which number did he say was prime? He was like 57 or something.
57, yeah.
It was like, let's in his proof, huh? And then it took a while going around to yeah. So anyway, what I want to say is that this actually gives us a very interesting a very interesting question. Is giving a cyclic group G, how many generators are there? Okay. So how many generators are there? That's a very interesting question, because we might want to know how many generators the group has. And you will see this has a very interesting connection with something else. We'll find out in a minute. Okay, so that's the question one. But I mean, one of the second question of this slide. We'll get to the second question. Let's now go through this, answering some of the other questions by seeing some of the properties of cyclic groups. Okay. So these are all like theorems that results that properties that I will state as theorems, and I encourage you to try to prove them. And those of you who struggle to prove them and want some sort of help, I'm willing to give you my a version of it. But you need to show me that you did it. I would like you to come to attend to the study session, for instance, and try to prove it. If not, you can also just look at online resources to see the proofs of this. That's also fine. But the first theorem is that indeed, giving a group and a subgroup of H, if G is cyclic, then H is also cyclic. So that means that every subgroup of a cyclic group is cyclic. Okay, so that's being answered. Okay, now here's something we will probably come back to this when we talk about symmetries and these things, the symmetric group and so on. In here, every subgroup of a cyclic group is cyclic, but it is possible that as a group is not cyclic, but it does have subgroups that are cyclic. Okay, so it's very important to note this subtlety here. I believe he's an example here. We'll come to this when we touch these other groups. We'll see some concrete examples. Okay. So it does not generate. We might have a group that's not cyclic, but under it, you should you should have a cyclic structure. And this actually tells us something also very interesting in here, which you will see in a minute. So for the time being, the second theorem is that given G, a cyclic group of order infinite, meaning that the cardinality is infinite, meaning that it has infinite element, then the theorem states that this G is isomorphic to the group of the integers, to the cyclic group of the integers Z. Okay, so in a sense, there is only up to isomorphisms. There is only one cyclic group, infinite with the thing. This actually tells us one of the challenges that I believe I was asking for is whether Q, R, and C are cyclic groups. So if these are, then you should be able to build an isomorphism between Z and them, right?
Oh, that's much nicer. I had a rather complicated proof that Q is not cyclic, but that's a lovely proof by contradiction.
Yeah. So this is the thing. So as you can see, from a classification point of view, is really not it's very interesting. This also implies that infinite cyclic groups are abelian, right? Because Z is abelian, so you cannot have a non-abelian cyclic group. Okay, so that's very interesting. And just on a comment on this guy again, going back to the Israel group, it's non-abelian, but however, non-abelian stuff, a non-abelian group can have a subgroup that's abelian, right? For example, the center. So just a side note there. So yeah, so infinite cyclic groups are certainly abelian, and as you can see, also this is the same generalizes to finite cyclic group. So every finite cyclic group is isomorphic to the group Zn. Okay. So that means that obviously that every cyclic group is abelian, whether infinite or finite. Okay. So this is very important. The thing. I mean, some of it you might have some difficulty in trying to prove and this, but just try. Even if you don't manage to come up, or you feel frustrated and this, but just having to try is already because you need to draw in a lot of the properties that we covered and possibly some extra stuff that maybe we didn't cover that you need. So this also gives you some sort of motivation for further research, right? Okay, so the next thing I want to cover, in fact, I will make a comment here actually before we focus on mod N. As I said, we want use cases for cryptography, right? So we need to start gearing up towards that. Okay, so before we go through these examples, to try to find subgroups, group structures under the mod N multiplication. Let's first make you aware that this notation Zn, this is, most of you will probably know this. In many books, they don't use Zn, they use this thing, this Z slash NZ. We call it the question notation. This is to do with we won't go through ring theory stuff, because of the I don't want to touch. It doesn't matter for you because you need a bit of a ring theory to understand this. So if you see this notation, it means Zn. Just view as Zn. Okay, it means the same thing. So in most books, especially in cryptography, people use this a lot. Okay, it means the same thing. Okay, and another thing is that Zn under is actually a ring. Okay. Most of you already figured it out. It's already a ring, and so it means that it forms a group under the additive notation, under the additive binary, under the addition only, right? It does not form a group under multiplication. Okay, so the question we ask ourselves, if Zn, if there is a way that we can cherry pick some elements of Zn, so that when we use multiplication mod N, we get a group structure. Is there a way of us cherry picking some elements? We know that the entire thing is not a group under multiplication, because not every element is invertible under mod N multiplication. It is a group under mod N addition, but it's not a group under mod N multiplication. Okay, so let's see an example here. So let's call this such a set Zn star. Okay, and let's consider an example, a simple example, Z3, obviously made of this, under mod 3 multiplication table given by this. So the question is whether this Z3 star being defined as the element 1, 2, forms a group under the multiplication table here that you can see. Yeah. Let's see a quick inspection to see if somebody has just the group stuff, the cyclic group stuff, whether it forms cyclic group. I'll leave that as a homework, or if you can answer also, that will be great. Does anyone want to throw the hat whether this forms this restriction, this cherry picking? So we have Z3, which is 0, 1, 2, right? And we have the multiplication table, the mod 3 multiplication table. So now we cherry pick two elements, the elements 1 and 2. Okay, so we look at the table here under the same table, under the same thing, whether this thing forms a group. Okay, Amir says yes. Who else wants to throw in the hat?
Yeah, I think by cherry picking 0 out of it, you avoid problems.
Okay. Yeah. Okay, yes, it is a group. Now, the question whether it's cyclic or not, I'll leave that for further thinking, whether it's cyclic. And if it's cyclic, which one is, can you identify the generator or the generators? Okay, so it's a group. Let's see again, Z4, okay? So let's see.
Ah, I think I see a problem.
Yeah. So does Z4 form a group? Is there any observation you want to make, George?
2 times 2.
Okay.
It's not even closed. The subset is not even closed.
Yeah. No, okay. Dimitri, it's okay. You can throw in the answers. It's fine. Or you can give it a chance for a few more because we have a few more examples to go through. So George, what's your take on this? So Barry thinks is this for this example that Barry thinks is a group? Is it a group? Okay, so Amir is saying yes to both.
My answer is I think it is not a group. The subset 1, 3 of Z4 star is not a group, I think.
Yeah. Okay.
Just you don't even need to think about it. Just look at that little multiplication shrunk down to the lower right 3 by 3.
Okay. It seems some people think it's not a group. It is a thing. But 2 is not in. Remember, so this is I'm not asking if Z4 is a group. I'm asking if Z4 star, sorry, this one, 1 3.
It's not even a closed binary operation, is what I'm saying.
Okay. Okay, so Amir saying that Z4 seems close.
Oh, Z4 is, but the
sorry, Z4 star. Amir saying it seems closed. Okay, I'll leave this as a food. I like when there is a split. Okay, we'll come back. You will be able to answer this by going back. There's a result further along that you will be able to come back and then decide whether this is a group or not. For the time, let's proceed again. Okay, what about this one? Z5. Z5 star, sorry. Z5 is the whole thing, but with the multiplication table. So let's say the ring Z5, and the multiplication of the ring, but with this Z5 star restricted by only these elements. So looking at the table here. Okay. Okay, so Dimitri already found a hack, which is that this is a field. Yes. So yeah, and he will probably, some of you already will figure it out. The hack is, when Zn is a field of a field, which is when n is prime number, then any non-zero element is indeed invertible. So so.
But again, I think this is true, but you don't need that. You can just look at the shrunken multiplication table.
Yeah. Yeah, I was just mentioning the other one because obviously Dimitri is.
No, Dimitri is quite right, but.
Yeah, but the rest, you are right, George. They don't need it. Just look at the table. This is the hint for you. Forget what a field means. Dimitri and George and the others know what a field is. Don't worry about that. Just look at the table. Okay. So it seems there is there a consensus then? Z5, this Z5 star is a group. If not, it's okay. I'll leave this as a point of discussion. This is what don't feel thing for anyone who have doubts. This is actually it's a good thing, you know. It's a good thing to go and think about it, and then you arrive to the conclusion. Ah, yes, now I got it. Okay, so don't feel shy about it, or feel bad about it. This is the whole thing of learning, right? So that's fine. Okay, let's go to mode 7. Sorry, mode 7, mode 6. Let's look at this table. One thing interesting you see is some of them have a lot of elements. Other ones have only few. Even though we are increasing the n is increasing. This is one of the reasons I want you to go and think about all this as you go along. But some of the stuff will you will have a hint in few slides of what's going on here.
I think it is very good to, for small n, have it down cold just through the multiplication table.
Yeah. Yeah. Just take your time and look at this, and look at the group axioms and see. Is there another one? The question also is is there another one that we can cherry pick from here that forms a group? If this doesn't form a group, who thinks it forms a group?
I think I see two smaller subgroups, but the thing as a whole, no.
Okay.
Oh no, wait.
Yes. Okay. Yeah, that's very interesting. Yeah, looking at the multiplication becomes harder as the order increases. Yes, it's true. It becomes cheaper, but that's why you will see a hack. There is a hack of how to make life easier for you, thanks to a bit of number theory. And I'm trying to avoid number theory as much as possible, because at the end of the day, this is an abstract algebra theory course. But at the same time, it shows how intertwined the branches, these two branches are.
Yes, that was a very nice example. I had to scratch my head a bit on that one.
Okay, so let's move on to the next one. So this is Z7 again, another prime number. I hope I didn't have any typo, because I was doing the slides very quick. Is this one Z star 7 form a group? Again, I guess you can make the same conclusion as what Dimitri was saying about if you know what a field is. But assuming you don't, you can just look at the table. For this to be a group, look at the group theorem. Group theory is axioms, right? It has to be closed. So that means if you multiply any two elements, it has to lie in there. The other thing is that it has to have a unit. Well, one is there. Yeah. Identity, one is there. Another thing, every element needs to have an inverse. Okay. That's certainly there. And you already know that Z7 is a semi-group, right? We come that under multiplication, so it's associative. There you go. Barry already gave a very interesting hint. Everything seems to revolve around things being relatively prime. Yes. 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 That's indeed the answer, Barry. So all the numbers from Zn, that are from between less than n, between n minus 1 to 1, that are relative prime to n, They are the elements of this z star. You'll see that in a thing in a formally. Here's a definition. Actually, this will give you more a hint for what Barry is saying. Okay, so for Zn, so we define Z star n as all the elements of Zn that have multiplicative inverse. This is what we've been trying to do to essentially. That's why I gave you the table. But another way of defining this is this: all the elements of Zn whose that who have this property of the greater the GCD of A n equals 1, meaning that they have the greater common divisor, which means between A and n is 1. Greater common divisor, this is number theory, meaning that the largest number that divides both. Okay. Yes, Dimitri. So another notation is also UN. Yeah. Obviously, we are reserving UN here for unitary for our purposes to not confuse it with the unitary group. But yeah, in the cryptography, in number theoretic notation, and even in cryptography, very often they use UN to denote this the multiplicative group of units. So they call it the group of units. So they call it UN. Obviously, for us. We also, especially in the quantum context, we have unitary groups, so the confusion will be like all over the place. That's why we are avoiding to use that, to not confuse people, to know that we are talking about, we are not talking about this in a thing. We are talking about unitary groups, but UN, be aware, can also have another meaning, like Dimitri is saying. Yeah. So this is it. So this is how you think. So if you have Zn, so this tells you how you cherry pick, how you essentially cherry pick, you construct the group structure out of the ring Zn. Okay. So this is what you do to put it less in an easy manner. This is how under the mod n multiplication. This is how you construct a group. So you pick all the elements of Zn that have a multiplicative inverse. In other words, the ones that when you multiply to that gives you 1, right? Or another way of seeing that is this: the ones that all the elements that have the greater common divisor of A and N to be equals to 1. Yeah. So the ones that are relative prime, that's another technical name for it, to N, as Barry was saying. Okay. So I think this is already like this is already will help you. Even this informal, this very informal definition here. With this already, you will be able to prove that Zn star is indeed a group under the multiplication, I claim. So as a challenge, you can go and double check that this is a group, okay? And then here's a challenge here. I really challenge you to go and try to think, if you can even go and look at the tables and then identify all the group elements, which essentially means just go check all the invertible elements of the tables, the ones that are invertible. And then you will have these elements. It's good to do this so you are familiar with the thing, with how these guys are constructed, because these guys, this group is very important in cryptography. Obviously, in reality, you have the n very large, right? It's not just a small n like this toy stuff. You want to make it as large as possible. Yeah. In fact, in the next session, I wanted to touch the discrete logarithm problem, but I didn't have time. I think next week we will talk about that from a group theoretic point of view, and also then it will lead us to the Diffie-Hellman key exchange protocol. Okay. So this brings me to another important thing. You're seeing already the connection between, I hope I didn't make typos here. There are probably typos somewhere, but you can actually, it's a good thing to correct me. George was already, George, you spotted something. George is eagle eye.
No, I'm just nodding. It looks good. It's just a different group theoretic definition of the phi function. I was just verifying it.
Yeah. So for a positive integer n, we define. So if you are a group theorist, so this is as George is saying, this is we are defining it from a group theoretic sense of view. This is also to see how the two branches of number theory and group theory can be intertwined together. The whole thing of interconnecting. There's a whole program called Langland program, which is about interconnecting different branches of mathematics and this. And Bourbaki tried this in the past also through the various type of abstractions and all this stuff. But there's still a lot to be done. And these are like just a toy example of how intertwined branches of maths are. So in this case, for a positive integer n, we define Euler's phi function. It's also known as the totient function. I hope I'm pronouncing it correct. George is my linguist tutor, my English tutor. So George, how do you pronounce this?
Yes, I would say totient too. So.
Yeah, totient. Yeah. So I'll call it Euler's phi function. So it defines. So if you have a positive, what is positive integer? You define it as phi of n to be equals to the cardinality of the group. Sorry, cardinality. Yeah, cardinality. Or in this case, I would say order to be more precise. With the group theoretic lingo. So phi of n equals to the order of the group Zn star. Okay. So the number of elements that this group has. So in theory, if you pick any positive integer, you have to construct the Z star group and then figure it out how many elements it does have. Okay, but there is a hack in finding, so you don't have to do that, which is what you see below here. Okay, but for the time being, in here, for example, so by definition, phi of 6 equals 2, I believe, because we have seen this example before. There's only 2. How many elements does the Z6 star has? Let's go back. I think we have an example here. Well, if this is a group, then it does have 2 elements. So that means this guy is 2, whereas 7, phi of 7 has 6, because as we see in this example, where is this? This multiplicative group, this Zn star, has not 7, 6 elements. Okay. So phi of 7 equals 6. Okay. Now, here's the hack I was saying, so that you don't have to construct. Life becomes easier when things are, things involve prime numbers. You start to see how prime numbers are really, when people say like they're like the building blocks, they show up everywhere. In mathematics, this is actually another good example for you to see that to see this. Even outside number theory. Look at this. All we want to know is how many generators are there in a thing on a group, on a cyclic group, right? This is an algebraic question. How many generators? I have a cyclic group. I want to know how many generators the group has. But then we need the number theory in order to hack the answer. So if n, if the n happens to be a product of power of primes, so these guys P1, P2 to Pj are prime numbers. And these guys, K1, K2 to Ki, are all positive numbers. Then we have this. So this is how you compute the thing, phi of n. If they are products of the thing, I pick here some random numbers. Maybe one of them or whatever might satisfy that. Maybe others. It might even be possible none of them will satisfy it. You have to double check. Or it will be the case that you have to do it the hard way, which is to actually construct the Zn star group instead of using the formula. George, you wanted to say something. You notice any mistake?
No, I think you say if n equals p1 to the k1 times p2 to the k2 and so forth, it's a theorem that every n can be expressed in that form.
Yeah, so if you know that, yes, there you go. That's why you should come definitely to George's study sessions.
It's a very beautiful theorem.
It is, yes, yes. I did explicitly mention it because of I'm trying to avoid as much as number theory as possible.
Yes.
It's actually a challenge to see if some people can find out which theorem is this as a part of the thing. Just figuring out what George just said to see if you can actually reverse engineer it. I mean, find it.
It's nice because often you can't reverse engineer, so this is a nice case.
Okay, George, can you repeat it? Yeah, Dimitri is very keen on.
Okay, my contention, I'll just put it out as a conjecture. The definition, part 3 of the definition, it is if n is in this form. And my conjecture is that all n can be put in that form. I'm sorry, I have to flip back and forth between seeing the slides and seeing the chat.
So George, Dimitri has a question. So your conjecture is saying any n can be expressed in this form. So you can always find prime numbers, blah, 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 and positive k that the thing. So any n. So then that makes life easy for us, right?
And also, this is a case where even this theorem only says you can find them, not how can you find them.
How to find them, yeah. One thing is there is, it can be, but necessarily to find those guys, that's the thing. That's another question, because you need those guys, you need these guys in order to compute the thing, right?
I have a little note for Crowdcast. If I go to full screen so that I can read the slides, I don't see a notification that there's anything in the chat.
Yeah, I noticed that too. Yeah.
The notification only shows up when you have the tiled screen, but then I can't read the slides.
Yeah, I noticed that too. Yeah, I guess it's a feedback to give them. They are listening because they check. Yeah. Yes, I believe that's the conjecture that George is saying. Yeah. For now, we call it in the community George's conjecture.
Yes, until somebody points out that maybe I'm not the first to conjecture this.
Yeah, and if it's true, then okay, life is easy for you because then you can just use. But the conjecture doesn't tell you how to actually find P1 and P2. You know, there might be other tools to enable you to do that.
But for this definition, if the conjecture is true, then phi of n is defined for all n. The totient function is defined for all n if the conjecture is true.
Okay.
If the conjecture isn't true, there might be an n such that Euler's totient function is not defined for that n.
Yeah. And then the question is, under what circumstances they think, yeah, for sure. Okay, so that's there's obviously you need that. You need find a way, efficient way for computing phi of this. I mean, nowadays, you know, I know some of you will try to. You can use software. Some of you will probably be tempted to use software. There are a lot of software stuff that do this for you, but it would be interesting if you can try to do, hack something like yourself. Okay, so another thing, I think this is not the only challenge. I believe there is another challenge, okay, which is this one. This is more of like the thing I think, if you look at it's more of like one of the properties of the totient function. You know, if n1 and n2 are two positive integers, is it true that they are multiplicative in the sense of, phi of n1 n2 equals phi of n1 times phi of n2, if and only if the GNCD of n1 n2 equals 1. Okay, so this is essentially asking whether you have the multiplicative property of the function if and only if their GCD equals 1 of the two of them. Maybe this will require a bit of machinery from number theory that we haven't gone through, but maybe if you think about it, even going through some examples, maybe you can at least figure it out, have some sort of intuition.
Yeah, I think the only if is a little trickier than the if.
Yeah. Okay, so this is it, really. So you figure out whether, is it if and only if or just if? Which one is easier? And I believe that's the last slide I have. As I said, the reason why we didn't cover much is mostly because I didn't have much time today to think. I finished work a little bit late to work on the slides. So apologies for that. But I promise you in the next session, we will start gearing towards, we will cover the Diffie-Hellman key exchange protocol. So we'll have two parts. Part A, we'll go through the stuff that we need, including the discrete logarithm problem. And then we'll define, the notion of a symmetric cryptographic system, and then we pose the problem of, how do you exchange the keys over an secure channel? And then we see how Diffie-Hellman key exchange protocol solves that using, the stuff, some of the cyclic properties of cyclic groups that we just went through. And then that's it. We should have enough of the cyclic groups. At least you will see how, we started from very abstract, and then we dive to this very interesting type of groups, like cyclic groups. And then you see how they are actually being very, very useful in maintaining our security. Obviously, we will also, I will touch on the thing, discuss a bit about, their exposure to attacks by quantum computers when quantum computers become available. So for now we are safe because quantum computers are not available. But if some of these guys manage to build a fault-tolerant quantum computer, anyway, we'll talk about that also, about the security of it and all this stuff. We won't obviously talk about we won't dive into much about complexity theory and these things because it's not the purpose of this crash course. But nevertheless, it's very interesting for you to see, a problem, a hard mathematical. This is how cryptography, modern cryptography is, right? It's about finding hard mathematical problems to solve. And then assume the security of it. Assuming that it's very hard, to solve it. Even if you have a lot of pieces of information, but there is one key piece of information that you don't have access to. It becomes very hard if you don't have that in order to think. And the Diffie-Hellman key exchange protocol is very beautiful, actually. I found it very fascinating to see, how this thing of sharing sharing key over a secure channel, because that's one of the things of thing I like about cryptography is the assumption that you don't never assume that someone else cannot intercept your communication or eavesdrop you. So assume assume that something will leak. So what you want to make it hard is for them, even whatever information they have, there is one piece of information that's hard for them to obtain on their own, even if they know the other stuff. So there is the incompleteness of the information that goes through that they are able to capture is what makes it a very fascinating field.
And for security, it means that there's a much smaller number of things you need to keep totally secret.
Yeah, exactly. Yeah. So yeah, so that's it. I know we haven't had much to cover, but I hope you kind of falling in love also with cyclic groups as we go through this. They do have other applications and these things. I just think cryptography could be a very interesting thing, especially to put it in the context of the quantum computation in terms of the impact of quantum computers in security in existing cryptographic schemes. So, is there any other question, or we just leave it here? And I hope to see some of you tomorrow. And I hope to see all of you tomorrow in the session. Does anyone need to know the link to join the session tomorrow? I can share that. It will be great to have as many people as possible, because it will just make it much more interesting to listen to people from different background, and also have different potential use cases.
Yes, and to show the rest of the world how diverse we are, so that anybody is welcome.
Yeah. So I'll pass the URL on the thing on. Okay, so Amir, are you planning to join the panel? Well, what I will do then, I will just be after my main presentation, I'll be calling people. So I will add you there too. I will look at who is present, and then I will just start calling people. And for those who don't want to join, or just if there is a question that shows up in the chat, just please help address them, because you've been with the community for some time, so you know pretty much more or less how it works. And some of the questions will probably be generic stuff about the logistics of it, how often the sessions are held, and so all this stuff. So that way we can reserve the discussion stuff and the questions and answers for some more interesting questions. Yeah, so yeah, any other comment, George, before we go?
No, I think this was short, but I think the challenges are maybe more challenging than we've seen so far. So I encourage everybody to get as far as they can on their own before the study session.
Okay. And do you want me to create again? Were you happy with the crowdcast? I will again create another, if you want, another study group session. So if you are holding one next week, anyway, if you are holding one.
Yes, I like now that I've worked out some of the issues, I like Crowdcast better than Discord.
Yeah, I like it too, because the fact that I could go and rewatch some of it, that's where I spotted some of the thing that you and Bob caught up, like the ambiguity and the definition of the exponentiation and so on, and some of the typos. Yeah, so it's also useful for me. So that way, actually, I can just go and watch the replay a bit, see what you are struggling with and all this stuff. It also gives me it's a way of having a feedback to see whether there was something I explained properly. Maybe I should explain something a little bit more simpler, or maybe a little bit more formal, something like that. Yeah.
So yeah, and if anybody has trouble with the arithmetic or number theory aspects, we can dive deeper into that in the study session too. Although this is an opportunity to learn some elementary number theory if you weren't familiar.
Yeah, that would be great, really. So that's why I really encourage you to join George in the study session. He will post. You'll normally post on Discord the time when these sessions are held, right?
Yes, I mean in the normal course, I have it at the same time as the lecture would be.
Okay.
So it would be noon Eastern time.
Okay. Okay, great. So if no other question, any final comment, George, we can just leave it here. And I just want to say thank you to everybody for showing up, and thank you, George, for helping out, and thank you to everybody on the chat for the engagement. And yeah, I look forward to the tomorrow's session and then the next session, the next live session we have with us. Okay, thank you, and I see you guys tomorrow. I hope to see you tomorrow. Now I need to figure out how to stop recording and then how to get off. Yeah. So yeah, thank you, George. Have a good weekend, everyone. Thank you.
Okay.